Welcome to session 9 in series Analog Circuit Design using ADS. This is Anurag Nigam. In this series I'm going to discuss some more gain stages, which are not just single stage gain stages, but they are like two or more stages. So first in the list here is Cascode Amplifier. Sorry. Okay. Okay. So Cascode Amplifier is made up of a common source amplifier followed by a common gate amplifier. So usually the impedance of a gain stage is GM-RDS square, as we have seen with the source degeneration, right? So in this case the current mirror should have a similar load. Otherwise, if you put two loads in parallel, then the load is going to be smaller than the smallest. So to avoid that, in this case, what I'll do is I'm going to use a wide swing cascode current mirror, which would look like this. Okay, so this is a wide swing cascode current mirror which I'm drawing. Okay, and this basically, let's say this is drawing some current, let's say 100 microamperes, and this is 1:10 ratio. So that means 1 milliampere will flow through here, right? Now we use another transistor which is twice the overdrive voltage, which means it is 1/4 the size of all these transistors, which is going to establish this voltage, right? So if we keep the current same, then the twice overdrive is possible if I use 1/4 the size. So this is 1/4 the size, and this will cause the impedance to look here to be GM RDS square. Now if you remember a source degeneration, let's number the transistors. Let's say this is 1, this is 2, this is 3, this is 4, and this is 5, right? So let's say all have the same GM and GDS, right? So but anyways, let's put here the output impedance here would be RDS 5. Just one second. Okay, it will be RDS 5 times of 1 plus RS. So RS in this case is RDS 3 times of GM 5 plus GMB 5 plus GDS 5. Okay, so now assume that this term is much bigger than this term, right? So I'll be left with, and then it is also greater than 1, so I would have the output impedance approximately equal to RDS, and let's say that RDS's are same, right? Just one second. Just one second. Okay, so what's going to happen is, let's say the two RDS's are same, then it will be equal to GM5 RDS square. Okay, so that's, and the GMs are all the same, so basically the impedance looking into this current mirror load is GM RDS square, right? Now if I consider a cascode amplifier, so it will be a common gate where VG will be decided here, and then there would be a common source, right? So now here, okay, so this Vi is going to be input to the common source, and then its output would be input to this common gate, and the output would be here. Again, the impedance here would be GM. So let's say this is 6 and 7, so it will be GM7 ds square. So overall the output impedance is going to be RO of the combination of mirror load and the gain stage would be GM, and let's say two GMs are same, so it will be GM RDS square by 2 because the two impedances come in parallel, right? So that will be there, and the gain AV will be equal to minus, okay, AV will be equal to minus GM RO, and it will be GM square ds square by 2, right? So this would be the gain of a cascode amplifier. So now the question is, how do you get the bias? So basically this, okay, will establish, okay, so let's say okay, so this will establish your VGS will be V overdrive plus VT. So that will be the input voltage, right? DC input voltage, and the output signal, right? It's going to be around your half the supply voltage, right? So in this case, what's going to happen is the okay, let's decide how much swing you want to give here, right? So this will be GM minus V over I plus VT, and the lower side would be established by VG, right? And that has to be established, VG has to be established with respect to here, right? So so we want to keep it in a high gain range. Just one second. Okay, so what I want to do is I want to establish here, okay, so most of the gain which you will see, right? Okay, so most of the swing we will see is I want to keep it low, so basically this voltage will decide the DC point here in the swing. So let me hold this down to like 0.7 volts, right, or 0.78 volts or something like that, right? So then this voltage would be something like addition of another 0.7, right, 0.6. So 6 plus 7 is 15, right? So let's say 1.6 volts here, 1.6 volts here, right? And let me establish this voltage by simulation, but usually it will be like 1.6 somewhere, right? 1.5, 1.6. So let's go ahead and put this in the simulation, right? So okay, so what I'll do is under gain stages new, and I'll say schematic, and I'll say cascode amp, right? Cascode amp. Okay, so now what I want to do is I want to take a transistor from a previous stage, maybe let's say any one will do, doesn't really matter. So I'm going to take this as is, right? I'm going to take this as is, and this also. So I'm going to just say copy. Okay, the label doesn't get copied, sorry. So let's just copy these, Control C, and let's go to our design and say Control V. Okay, so now we have over here, we want to construct a current mirror first, a wide swing cascode current mirror. So I am going to just, this is a 1:10 ratio, right? So okay, so what I'm going to do is I'm going to repeat this stage on the top, just like when I designed earlier in the previous session, right? So now I have this like this, and this is my supply voltage, and this would be connected over here, and here I will draw the current out. And next is I want another transistor which is 1/4 the size, so I'll just copy this one over here, move the supply out a little. Okay, here what I want to do is this has to be 1/4 the size, right? So just 1 second. Come on, let's put this again. Okay, and this will be diode connected like this, and this will be connected over here. Right, now the current I'm going to draw is going to be the same. The current I'm going to draw is the same here, 100 microamperes, right? And this is 1/4 the size, so I will make this as 1.25 into 1. You can make a 0.65 into 2 also, right, for the layout consideration, right? And then what I'm going to do is I'm going to choose 1/3 the size, which is over here on okay, so here this is almost 1/3 the size, right? So I'm just going to say edit, copy, and I am going to paste this over here, edit, paste. Right, so this is going to be one stage, which is a common gate. This is going to be a common source. Now I am going to do a static analysis on this, which means I'm going to do a DC analysis on this one to establish a correct bias. I'm going to keep this voltage as 1.5 volts, so I'm going to choose VG as 1.5. 1.5. Okay, I establish VG as 1.5 here, and here I'm going to do a sweep, so I'm going to do a V in. So I'm going to copy this here, and I'm going to sweep V in onto the gate like this, and this is the VO, so I'm going to name this as VO. Okay, so now we are done with the Cascode amplifier. So all I need to do is declare a variable which is V in with some default value, right? V in with a default value of 1, and I'm going to sweep it anyways, and then I want to place in the include file here. So that's the include file here, and then I'm going to do a DC sweep, right? Simulation DC, and I'm going to sweep the DC voltage, and I'm going to go from 0 to let's say 2 point, or rather 2.4, it's okay. So let me just sweep V in, I want to sweep from, so this is a capital V in, right? So this is not case, this is case sensitive, so type the same thing from 0 to let's say 2.4 volts, 2.4 volts, and I'm going to do a step size of 0.001. Say okay. So this is my sweep, and I'm going to observe the output voltage. Okay, and what else? I think I'm all set, right? So I'm going to do a simulate. And I'm going to do a plot, VO versus VN. So you see that this is a extremely high gain, right? And the question would be around 1.2, so I'm getting a good swing. It's just that over here I'm going to lose twice of V overdrive here, right? Because this is a wide swing cascode, right? So this is my design. Let's see what is roughly the gain. So I'm going to put a marker over here and a marker over here, and the marker the quiescent. The quiescent is around 1.2, right? The quiescent is around 1.2 output, right? So let's see. Yes. Okay, so I would have to probably increase the number of steps in simulation because the gain is very high, right? So what I'll do is I will just do 10 more divisions per sweep. Okay, and just say simulate, and here I want to establish 1.2 or 1.25 or something like that. So I think this is my good quiescent point, 1.275. so I can put here another variable Vn. Okay, so this Vn I can keep as whatever is the input voltage from my simulation. So this is around 0.609, right? So I'm going to put that 0.609, 0.609, right? Apply. Okay, so I'm done with that. Okay, so now I'm ready with the AC simulation, but let's okay, so you can figure out the gain using the slopes here as we did earlier, or I can directly do the AC simulation. So what I'll do is I'm going to just go ahead and save this file, save as, and save this as AC, and so this is saved as AC here, right? So I'm going to throw out this one, and I'm going to put a AC source. So I'll go to sources, frequency domain, and I would put here VAC, and the thing to remember here is that DC value is Vn. Okay, Vn volts. So once I'm done with this, I have input as 1 volts. This is a AC simulation. I can throw this out and put here simulation controller as AC. Okay, notice how would you compensate this, right, for a given phase margin? Of course you can do a lead compensation on this stage, but in this case you would have a capacitor and resistor to ground for the common gate in case you need it. So let's just see if we have a margin. So what I will do is I will do a log sweep from 1 Hertz to 10 gigahertz and 80 points per decade, right? And then what I'm going to do is in the display I'm going to display how many points per decade. So that's 80, correct? And here I want to display what is my DC value, Vn, correct? Now I'm going to hit simulate on this one, and what I have over here, so I can plot the gain, which is going to be the dB of V out because the input is 1 volts, right? Okay, and here I am going to do a log scale on x-axis. So a log scale on x-axis. So here you see the gain is much higher, right? So the gain is around 54 dB, right? So that's what you are expecting here, GMRDS square by 2, and then you are also going to put in here the phase. So the phase over here would be here. Let's have a look at this phase. Okay, so now here if you see here, the gain doesn't roll to 0 and the phase has rolled cross 180, right? Because it will start at 180 and it has lost all the margin over here. So what I would do is I have two options. One is over here, but this is not a gain stage, right? Because this is seeing a load of 2 over GM, right? So I would put here an RC here. So that would be a form of compensation. So I may not be right, but my instinct says that RC over here would do that. So I'll go to lump components and I will put here, let's say, a certain kilo ohm. Okay, so let's say I'm going to put here 900 ohms, let's say, and a capacitance of, let's say, 1 picofarad is okay. And then is this connected over here, and this is connected over here. Now if I was to do this, nothing has happened here because this has to be shifted down, right? 180 degrees. Okay, so this is not doing much, so let's see if this was over here. So I'm learning along with you. Let's see where the compensation is going to help. So I'm going to delete this one, and I'm going to take this compensation across here, right? So I guess this would stabilize the first stage, and I expect that this would be stable. Or I would need both of them. Let me just see. Let me just put a tune on and see the behavior. Okay, so I am going to tune this guy, and I am going to tune this one. Okay, so let's see the response here with these two tuners. So this one is not doing much, it's just worsening the margin. Okay, so this is not doing it. Okay, let's see if the capacitance is large, and what happens here. Nothing much. This spine is not moving at all. Let's kill the gain. No. So let's put here 5k. So what is it gonna do? Nothing. It's just going to make your corner frequency worse. That's all it is going to do. This is going to affect a little bit of gain, but then it also affects the phase. So upgrade schematic close. Yes, let's try both combination. According to me, you cannot put anything across this stage. Okay, let's try that, because anyway, if you do not have a margin, you cannot use this very high gain stage amplifier. So let me see if I'm recording this. Yes, I'm recording. Okay, so I'm going to simulate this again. Okay, slight improvement, but not much. So I think I have stabilized these stages earlier. I don't think that you do it between input and output, because I think that doesn't solve your problem, but let me just give it a try. I'm as blind as anybody else here. Let's see what happened over here. Nothing. Okay, it had nothing happened over here. Okay, so now we don't have much choices other than I am going to run a tune and see if I have a right compensation. Okay, so let's see. This is my stage. What does these do? Okay, this is killing the gain, right? This is going to kill the gain. Okay, these two are going to kill the gain. What about this? This is doing nothing. C1 R1 is doing, yeah. Of course, you have some margin here, but not sufficient margin. Okay, so this margin is not sufficient. You should be somewhere over here, and this should come down. So let's say this is 200. Okay, let's come down further. Okay, so now I might have crossed over here, right? So the crossover is over here. Just one sec. Okay, so this is the one which is going to kill it, and this is not going to do much. So as I suspected, because you're not going to get any gain out of the this stage, most of the gain is coming from here, so the compensation has to be from here, right? So in this case, let me put a marker here, which is right click marker, this one. Okay, so let's see at the crossover. The crossover is somewhere over here. In here I have 124-degree margin, so that's fine. Do I have to kill the gain so much? Let me see. Okay, let's see how much gain I can kill and how much margin I can have. So this is still 1 degree, and this is 83 degrees, so it is too much of stuff which I have killed. Okay, so let's kill some more. So just 1 second. Okay, let's see over here. How much margin have I killed it? Okay, I have around 100. Okay, up to here. Okay, I have around 115 degrees margin over here. And the first corner frequency, let's see that. Okay, so the first corner, so basically what I'm saying is, okay, so let's see the first corner frequency. Let's put a marker new, and this is my gain stage, right? So 54 has to become 51, so roughly over here. So I am having 2.3 megahertz, which is too, I don't want to compromise that much, but if I have to, then I have to. So this is going to change the corner. This is directly affecting the corner, and this is doing nothing. Actually, this is doing nothing. So this is doing nothing to the corner. Let's see a compromise of 2. So corner doesn't change here. So 97-degree margin, 80-degree margin, and the corner, this is for third 54, so I have to go to 51 point something. 51 point something is over here, so 2.9 or 3 megahertz. So this is a gain stage which will be usable up to 3 gigahertz. I'm gonna update this, and this is my response. So I'll just update you on what happened on the circuit side. Okay, so I have a compensation here. I have a compensation over here, which is around 0.5 and 440 ohms, right? So this is that compensation, and this stage will be usable up to 3 megahertz, which I don't like, but that's what I have in the first cut design, right? So let's just get rid of the tune portion of this and the tune portion of that. So roughly the feedback resistor is around 450 on both, but this capacitance is higher or smaller. So at present the first cut design would be like this for a Cascode amplifier, and the corner is around 3 megahertz, and the margin is going to be around, the margin is around 85 degrees roughly. So this is the design of a Cascode amplifier. So I'm going to stop here. In the next section I will pick up differential amplifier.